All right, let's get to the meat of today's lecture. This is the really interesting part. Here is a statement of Stokes' theorem. I'll cover up the bottom part. We'll get to what all of this means in a second. There are a lot of assumptions that go into Stokes' theorem, and for this class, I'm not going to worry that much about the assumptions, but I do want you to be able to apply the assumptions correctly to be able to compute the correct answer. So I'm not going to give you tricky functions to try to trick you that don't satisfy some of Stokes' theorem. Anyway, assume that S is a surface. This surface needs to be oriented and piecewise smooth. Oriented just means that it has a normal vector. Piecewise smooth, I want it to be differentiable everywhere. It's bounded by a closed curve or a finite union of closed curves. So the finite union of closed curves, looking back at these surfaces, we see that this is one that's a finite union of two closed curves that I want them to start and then stop again. And this one's one that starts and stops. You'd have to get a pretty crazy surface where the boundary doesn't ever end, so you can't have infinite boundaries. And we want the boundary to have positive orientation. The surface lies to the left, like we talked about before. Also, we're going to have F be a vector field in R3 with continuous partial derivatives. Then, and this is the cool conclusion, if I want to look at the line integral along the boundary of S over this vector field, I no longer have to compute the line integral if I don't want to. Instead, I can compute the double integral over a surface as long as that surface has the boundary that was the line integral. But when I compute this integral, it's over the curl of F rather than the original function F itself. So what is all this saying? Over here, I have a vector line integral, and I usually parameterize that line integral by some vector function C of t. That's going to parameterize the boundary of S. This little curly thing is just saying the boundary of S. And over here, we're taking the vector surface integral over some surface, so we're going to have to parameterize a surface, and that surface has to have the same boundary as this line integral. And then I can take the double integral over the curl instead. So these are sort of the generic ways of writing it. Here, this is the way that we would write it if we were actually going through the act of computing it. This is a review of line integrals. Remember that if I'm taking the line integral over a vector-valued vector field, and my boundary is parameterized by some path C of t, it's just going to be f of C of t dotted with the derivative of C of t. And these are the bounds on t. And in this case, maybe I'll draw a picture. That's going to parameterize some closed boundary. This is my C of t path. Or I could take the double integral over this surface, so I'm going to have to parameterize this surface. And I could take the double integral of the parameterized surface. How do I compute surface integrals? Recall, for surface integrals over vector fields, you need to take, in this case, it's the curl of F. So I take my function, I evaluate it along the parameterization of the surface, and I have to dot it with the normal vector. And that's going to yield the same thing as this vector line integral. So I just said a lot. I'm going to say a couple of comments on this theorem, and then we're going to do an example. So my first comment is that this is absolutely nothing new. This is exactly the same thing as Green's theorem. That Green's theorem is just the flat version of Stokes' theorem. We saw with Green's theorem, we're taking the line integral along the boundary. It's the same thing as the double integral, but we had to do this dp dq stuff, and this dp dq stuff is exactly the scalar curl. So the curl of f, if I'm thinking of f as just being a two-variable vector-valued function, that's what this would be, the scalar curl. Great. So thankfully, this is nothing new, and really it's just different notation for the exact same type of concept. The difference is that Green's theorem lives down in R2, And Stokes' theorem can be boundaries that are up in R3 and surfaces that are in R3. In R3, whereas Green's theorem has to lie flat in R2. The second thing that I want to mention that's a consequence of this theorem is the surface independence for curl of vector fields. Notice that in Green's theorem, maybe you can't hear me, notice in Green's theorem that the surface, it doesn't really matter what surface we use as long as it has the same boundary. That means that if I have some boundary that looks like this, and I compute the surface integral over this sort of flat-looking surface, it'll give me the same value if I use the same boundary as a surface that maybe had the same boundary that went up much bigger, or maybe some surface that went down and sort of, looked like a cone. That the curl of f over each of these surfaces is going to yield the same value. That means that, and that's what this states, the flux, which is the vector integral through these surfaces, depends only on the oriented boundary, written delta s, and not on the surface. And a final consequence that's cool is that if S is closed, if I'm evaluating the curl of a vector field over some closed surface, then this will always be 0 because there's no boundary. So the boundary integral must have been 0, so this has to be 0. All right, that's all of the theory that I want to do. Let's go ahead and see how Stokes' theorem works in an example. So I want to compute a vector line integral over this vector field where the boundary in this case is the intersection of this cylinder with this plane. The first thing that I want to do is draw a picture of this. So what is this cylinder? The cylinder x squared plus y squared equals 1. Z is unrestricted. It's going to be a cylinder of radius 1, and the xy plane is where the circular portion lives. So this is my x, my y, my z. The plane z equals y plus 1 means that when y equals 0, z equals 1. Let's find a point on this cylinder because I want the intersection. So let's look at the point where y equals 0. When y equals 0, z is up here at 1. When y equals 1, z is down at 0. So it means we're parameterizing something that sort of looks like that. As I intersect this with this plane. So I have two choices. I can compute this directly, which I'll show as an optional video next, or I can compute this using Stokes' theorem. I'm going to use the fact that by Stokes' theorem, this single integral over this boundary is going to be equal to the double integral over the curl of f over this parameterized surface. So maybe I'll write, the curl of f, maybe I'll write dot ds. Sorry, for formal notation. So how do I compute this? First I need to come up with a parameterization of this surface. What is the surface that we're talking about? I'm just going to use the flat surface that has this as a boundary. And there are two different ways that I can think of parameterizing this surface, and you can decide which of the ways that you like. But you could think of parameterizing the circle down in the xy plane and then giving it variable height, because the height in this case is going to be y plus 1. And that's the way that I think I want to parameterize this surface. So C of u, v I'm thinking of a whole bunch of different radiuses that get bigger and bigger until they go out and hit the boundary, meaning that I need a variable radius, so I'll call my radius value u, and v is going to have to be my angle that I sweep out. So I have u cosine v, u sine v. That takes care of my circles. And then my variable heights, in this case, z equals y plus 1. So my z component is going to be y, which is u sine v plus 1. This is a nice parameterization, I guess. What are my bounds on u and v? My u is the radius. The radius starts at 0 and gets all the way out until 1. So 0 is less than or equal to u is less than or equal to 1. And v's are going to go from 0 to 2 pi. This is one way to do it. You could also parameterize this as a magic carpet function and just have really messy bounds. But I think that this, for me, is an easier way of thinking about it. So to apply Stokes Theorem, I have to find the curl of f. This is going to be the double integral as u goes from 0 to 1, as v goes from 0 to 2 pi, of the curl of f evaluated at our parameterization. I haven't done that part. Dotted with the normal vector, dv, du. So there are still some pieces missing. I've parameterized this. I need to find the normal vector. I also need to find the curl of f and plug in my parameterization. So let's do that piece by piece. First, let's find the curl of f. Maybe I'll do this on a separate sheet of paper. So the curl of f, recall that's going to be our del operator crossed with f, which is I, j, k, d, dx, d, dy, d, dz of our f function. I need to relook at that. And our first component is 4z. Our second component is negative 2x, and our third component is 2x. And hopefully this will simplify. That's one of the cool things about computing the curl in these cases, is that you sometimes get things to drop out. So the partial of my third component function with respect to y is just 0. The partial of negative 2x with respect to z is also 0. So yeah, things are starting to drop out already. J, the partial of 2x with respect to x is just 2, and the partial of 4z with respect to z is 4. Finally, the partial of negative 2x with respect to x is negative 2, and the partial of 4z with respect to y is 0. So that means that in this case, the curl of f gives us a new vector that's the vector 0, comma, 2 minus 4 is negative 2, that's negative, so that's positive 2, comma, negative 2. And we got lucky in this special case that when I took the curl of f, I got something that was a constant. So I'll write this down. The curl of f in this case, 1. We computed the curl of f, and we got just a straight up vector, in this case the vector 0, 2, negative 2. But you could imagine that given the fact that these functions have x, y's, and z's in them, this might have x, y's, and z's within the curl function. And then if we had those x, y's, and z's, we would have to plug in our parameterization to take care of that, because this integration is with respect to u and v. You need to plug in your parameterization to eliminate the x, y's, and z's and replace them with the functions of u and v. But we're getting there. Now we have to dot it with the normal vector. So we have to compute the normal vector. recall that our normal vector is just equal to the cross product of our tu and our tv, which is the partial derivative of our parameterization with respect to u crossed with the partial derivative of our parameterization with respect to v. Let's write out what each of those functions are. In this case, maybe I'll write it over here. Recall that our parameterization in this case was given by u cosine of v, u sine of v, u sine of v plus 1. And you could parameterize this differently, but this is the one that I chose. That means that the partial of this with respect to u is going to treat v as a constant. So if u is my variable, this is just a coefficient, and I am left with cosine of v, sine of v, sine of v, my partial with respect to u, and my partial with respect to v, treating u as a constant, is going to be negative u sine of v, u cosine of v, and u cosine of v, because the one just drops off. Let's take the cross product of these two vectors. So n is equal to tu crossed with tv, which is equal to I, j, k of cosine of v, sine of v, sine of v, negative u sine of v, u cosine of v, u cosine of v, which is equal to I sine u cosine of v, sine of v, minus sine of v, u cosine of v, minus j times u cosine squared v minus negative u sine squared v, I ran out of room, plus k times u cosine squared v minus negative u sine squared v. This looks really long and messy, but thankfully a whole bunch of things are going to cancel, right? So here I have a u cosine v sine v. Here I have a minus u cosine v sine v. This is actually just 0. In my next component function, I have a negative j. Sine squared plus cosine squared is 1. I factor out this u, and I'm left with just a negative u. In my third component function, similarly, cosine squared plus sine squared is 1, and I factor out a positive u. Da 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 da. So thankfully, in this case, we found a normal vector. And for this normal vector, it's in terms of u's and v's. And something that I might want to verify is this normal vector positively oriented? Is it pointed up? And we see that the z component is positive and the y component is negative. So it means that it's pointing up in the z direction and negative in the y direction. So it means that either this picture is off or this normal vector is a little funny. I will get back to you on that one. But let's finish the computation. So we're going to dot this with a normal vector. So although this problem is long, none of this is really difficult. It's just putting together all of the pieces that we did before. Finally, we've set up the integral. How did we set up the integral? First, we parameterized the surface that had the boundary that we wanted. Next, we computed the curl of f and made sure that we evaluated it at our phi function. And then finally, we found our normal vector And now we're just going to complete our integration by taking this dot product and computing the integral. So when I dot these two functions, I end up with 0 minus 2u minus 2u, which is negative 4u, dv du. Double integral, I'm going to pull out the negative 4 in front, negative 4u dv du. Integrating with respect to v, I get negative 4 uv, evaluating v as v goes from 0 to 2 pi. That ends up being 2 pi times u, or negative 8 pi u. This is also evaluated as u goes from, no, integrated as u goes from 0 to 1 du. So that becomes 1/2 u squared, or negative 4